Welcome to the Misadventures of the Evergiven. You've all probably been following the fact that there's this large container ship that has got itself stuck in the Suez Canal, and they're scrambling to try to figure out how they can free the vessel. It's stuck diagonally, and the Suez Canal is reasonably deep at 24 meters, but nonetheless, it's still a very narrow, very shallow area for a boat to be stuck in. So they're currently trying to dredge, dig around it, push it free with limited success. The Suez Canal is a vital shipping lane because you can see it provides a shortcut through Egypt along the Red Sea. Ships can go up through the Gulf of Aden into the Red Sea and out through Egypt rather than going all the way around Africa. So it's a considerably shorter route, and it's, of course, then very important, and it's caused a backlog of shipping. The canal itself is really fairly short. It's flat. There are no locks, and the ship has got itself stuck just a few kilometers inside the canal. It's hard to get the idea of the scale of these vessels. The Evergiven can carry 200,000 tons of cargo. Not the ship, that's the cargo, 200,000 tons. There are 20,000 of these containers on, of the 40-foot variety that will fit onto a transport truck. So there is an enormous load, and we need to put that into scale a little bit. The ship, if stood next to the CN Tower, would reach the observation platform. So it's as tall as the CN Tower is for visitors, right, up until that revolving restaurant. And the little red stick I've shown is to scale. It's a very large vessel. There's approximately 40 million Canadians. If every one of us showed up and said, we'll carry something away, we would have to take 5 kilograms of cargo each for every last citizen in Canada to unload the vessel. Put it another way is we eat about 1,000 kilograms of food per year per person. This ship could carry 200,000 years worth of food for a single person. Yet another way of looking at it, it would feed all of Canada for 2 days. The 20,000 containers would take more than 300 barges to remove on site, and I'm not sure what you'd do with them. Stack them in the sand, take them back out to the sea, put them on another ship. Unloading a vessel of that size where it's sitting is not like an easy task. They are typically unloaded at ports with infrastructure, trains, trucks to pick it all up, and it's still a mighty undertaking, not smack in the middle of the desert. To give you a final scale of how much cargo this ship carries, this is Carrier Strike Group 3. During Operation Enduring Freedom, these vessels have a total weight of 248,000 deadweight tons, slightly more than the cargo capacity of the Evergiven. So I've modified this picture a little bit. We'll take out the 2 French vessels, de Grasse and Charles de Gaulle, and the reduced carrier strike force. The Evergiven can carry a cargo weighing as much as this entire aircraft carrier strike force. 2 full nuclear aircraft carriers and the complement of support ships. So we're talking an unbelievably staggering amount of cargo is on these vessels. And that's how they're currently got their best idea to dig it out. And you can see that this is problematic if you're going to be going at it in this manner. This begs the question, what did they do in the past? When ships went aground in the past, how on earth did they get them out of their predicament, if they could at all? And history shows our ancestors, while they may not have been educated like we are, they're still very ingenious people. And ships running aground have been a problem for centuries, and it drove a lot of physics forward. The problems with longitude, GPS systems, to keep people from foundering, dying at sea. There's been a lot of applied science for many centuries trying to deal with this. This is one of my favorite of the Romantic era paintings, the Raft of the Medusa, another ship where the people were like left at sea, and of course it's probably a lot nastier than the painting shows. People in the past had to be much more clever than us to do things that we take for granted. So one technique that they used to use to retrieve things is called the tidal winch. So if we look at our barrel stuck in the mud at the bottom of the ocean, and we want that barrel back. So what we would do is float a barrel on the sea at low tide. And the barrel would be of various sizes, right? You might just be trying to recover your ship's anchor that you lost, and you want it back. So you get a barrel that's, the size of a good-sized rowboat. You put it out there, you tie a rope onto the submerged cargo that you want back, pull the rope really tight, and when the tide comes in, you just might be lucky and pull that thing out of the mud. Maybe you only lift it a foot. So then what you do again is you wait for the next low tide and you pull that rope tight again. And eventually you budge your cargo off the bottom, and then you can winch it up to the surface. You can imagine this is a fairly protracted effort to do this. On something as big as a ship, they used another technique. They made gigantic satellite boats called camels that they would tie to the side. The camels would be flooded with water and submerged, tied to the vessel, and then you would pump the water out of the camels, and the camels would attempt to rise to the surface, and they would lift the boat, and you could get the boat free of a sandbar or where it was stuck. This, of course, is Archimedes' principle. And it's got a fairly simple formula. The buoyant force is the density of your liquid, mu, times gravity, times the volume. Well, the density of water is about 1,000 kilograms per cubic meter. So a refrigerator totally filled with water would weigh about 1,000 kilograms. So we're looking at a buoyant force in the neighborhood of 10 to the 4th newtons per cubic meter. These camels were unbelievable engineering structures. Here's an example built in a museum model. You see all these little winches and levers and things that would be attached to the ship. So this is no small undertaking to build these camels. You can see what they've done here is they've woven large support beams or sponsons, and they've gone right through the cannon portholes, and they've put up riggings here, and this camel's going to be tucked to the side, flooded with water, and they pump the water out, and up she'll come. Here's a look from the inside. So the things were almost pieces of artwork, and you can imagine the effort to build these was by no means small. And this is what I mean by just the ingenuity and the willingness to do hard work. And here we see a great application of all sorts of laws of the lever, we've got tension in cables, we've got buoyancy. It's really a fantastic example of applied physics, but in many cases, these people would never have heard of Newton's law. This was a technique passed down from shipwright to shipwright, from nautical engineer to nautical engineer over the centuries, that we can now look at from the pure scientific point of view how these things worked. The War of 1812, the section of it that was between Canada and the US, part of its fate was decided by camels. The American fleet was trapped in Erie, Pennsylvania, in a harbor called Presqu'Isle. And the Presqu'Isle Park, to this day, you can see the situation. It's a lovely harbor, a narrow opening. I don't know how big it was historically, but there was a sandbar across it. And the American ships were stuck in the harbor. They'd built the ships, but they couldn't get out because the sandbar, you could walk across it and you'd be head and shoulders out of the water. The British fleet were outside guarding the harbor, but they couldn't get in to attack the American ships. So there was a stalemate. But Barclay, the British commander, at one point, he left to go to basically a party. And the fleet left, and Perry seized the opportunity. They built camels, and they started floating their fleet across the bar. When the British commander came back 4 days later, he was stunned to see the American fleet was out. Unfortunately, they actually weren't out, and had Barclay attacked, he would have wiped out the American fleet. The really big armed ship was still stuck on the sandbar. So Perry, in desperation, ordered the remaining fleet to put sail and head out at the British, and he started making a commotion on the decks of his flagship that convinced the British the fleet was in fact all out and all able to attack, and the British turned and ran out into the deeper water, and Perry's fleet got loose, which caused the failure of the British fleet, which caused Amherstburg, Windsor, the whole southwestern field of battle to be lost, and Canada lose a good chunk of Ontario in that year of the war. So it was a major, just strikingly good effort on Perry's part, and he used these Camels to lift his boats free. The labor is unimaginable, what they would have had to have done to do that. And Perry's victory, of course, is celebrated on the U.S. side, and I'll give him credit. It was a damn good piece of engineering to pull off what he did. So, could we use Camels on the Evergiven? Well, let's just take a ballpark figure, some basic back-of-the-envelope physics. The Suez Canal is at maximum 24 meters deep, and the Evergreen is 400 meters long and nearly 60 meters wide. So just doing a crude sketch on it, I can fit the shape of a camel that's the same width of the ship and half as long on the picture. So that'd be about as big as you could berth on either side of it and actually, float it and still turn the thing so it fits inside the canal. So the question is, how much buoyancy could we get out of these Camels on the side? So what we have to do is do some basic estimating. I'm going to assume we can make Camels that are as wide as the Evergiven, half the length of the ship, and we'll make them 20 meters deep, so we've got some depth on the bottom. If I calculate the volume, I get 232,000 cubic meters of displacement in these Camels. And that would give us a calculated buoyancy force of about 5 billion newtons for 2 Camels. Now, if we take any force in newtons and divide it by gravity, that will give us an equivalent kilograms. So 5 times 10 to the 8th newtons, 5 billion newtons, is 500 million kilograms equivalent. And that works out to be 500,000 tons. This is double the GWT, or the gross carrying capacity of that ship. So even if I'm off by a factor of 2, 2 large Camels should be able to completely offset the cargo and lift the Evergiven. Now, by how much would it lift it? Now you got to talk to a nautical engineer. The shape of the ship, there's all sorts of calculations in her ship's basically manual that was created, and I don't have access to the stuff. And if I did, it's not an easy calculation. So the question is, these Camels of about this size could be put alongside her and would completely offset the weight of the cargo, meaning we don't have to unload the cargo. So could we use this ancient technique to free the Evergiven? My guess is not a chance. They do have very sophisticated floating docks now that make the early Camels look like pieces of crap, really artistic pieces of crap, but basically not very sophisticated. But they're monstrous docks that envelop on either side, and you'd need 2 of these to come at either end of the Suez Canal, literally one of them coming out of the Mediterranean, one of them coming out of the Indian Ocean somewhere, and having to meet up and find the room to lift that vessel. So my guess is what they're going to wind up doing is unloading the vessel with the cranes they have there. I'm just not sure where they're going to put the containers. But just to show you that there are all sorts of really innovative techniques. Now, can you imagine the very first person that proposed building one of those Camels to lift a ship free? How much they would have laughed at them. So it's a very interesting engineering problem. It's basically all applied physics to try to figure out what to do with this ship. So there's our little science moment for the evening.